So now in this video, we're going to start our construction of a left hard measure. So first of all, we want to define it on those compact sets. Okay, so from last time we defined this, if you recall, in the last video, we defined for each open set mu v, we defined it over the compact to be the number of v you require to cover this k, normalize it by some other factor, the covering of some k0. So the idea is that when v becomes finer and finer, the whole thing will converge, okay? To show this converge is actually fairly difficult, so we do need a little bit technical lemma. So let's do the following. So let's let curly k to be all the subset k in G where k is compact, okay? It's just a huge set. But let's do the following. So last time we saw that this mu v of k is going to be less than equals to this index k over the interior of k0. Okay, so it's bounded above. So each of these mu v, well, one way if you think about it is a function from k to the reals. Another way is basically you can think about it as an element inside a product space where each copy corresponds to some element in the compact. So let me explain what I mean. So let's define the following. Let's define a huge space X, okay, by the following. So I want to take a product space where for each compact set K inside my group G, I want to product a copy of a closed interval, so from 0 to this k over k0 interior, okay? So this is, each one of them is certainly compact, okay? So this is a closed bounded interval. So this is a compact space. And you're taking a product of potentially uncountably many of them, but it doesn't really matter. Tikhonov theorem tells you this whole product space under the product topology is a compact space. Okay, so we're applying Tikhonov, saying X is basically compact. Of course, we also need an axiom choice to make sense of this infinite product. Okay, so everything we are assuming the axiom choice for sure. Okay, so this is a huge space, and each of these mu of v can be think about as a element inside this X, okay? So for each of these mu v is contained in X, okay, by the following embedding, I can just treat it as mu v on the kth copy. I evaluate its value at this compact set K, so K is inside compact, okay? So in this way, all these mu v function, we can think about it as an element inside a compact, may not be metric space, but a compact topological space. Okay. All right. So now let's define the following. So let's make the following definition. So I want to say, well, I want to show that as v kind of goes to the identity, goes to smaller and smaller, I get something that's basically converge to somewhere. Okay, so how I translate as an idea into the space X is the following. So let's C of V to be the following. So I consider all those mu of U where U is an open set and containing V. Okay, U is open. So that's going to be a subset in X. Okay. So each of these mu U give you some element in X. Okay, you take all of them. And then you want to take their closure, okay? So because X itself is compact and you take something closure, so you get something that's also compact, okay? So each of these C of V is also compact. And moreover, I want to show the following. So if you have any finite collection of V, so let's say V1 up to Vn inside their open neighborhoods of the identity, so E is in here, they're open. Then because if you consider their finite intersection, I go from 1 to n of these vi, so this is finite intersection is still a neighborhood, open neighborhood of the identity, and is inside each of these v of c of vi. Okay, so you know that c of vi, their finite intersection are going to be non-empty. Okay, so for every finite collection of these vi, the C of Vi is not going to be the empty set. Okay, so you have something non-empty, and because you have something that's compact, you have this finite intersection property where any finite intersection of your compact set is non-empty. So you know the entire intersection is non-empty. Okay, that's from basic topology. So you have the intersection of all the open sets where open neighborhood of E. You intersect all of these C of E. That's going to be non-empty. Okay, so this whatever is in there, it looks like a limit of this mu of V. Okay, so an element inside this intersection is an element of X. I can treat it as a function from K to R, where each mu of K is inside the corresponding interval, and that looks like the limit of our mu of V. Okay, and that's going to be our candidate for a hard measure. Okay, so let's fix. For now, let's just fix any of them. So let's fix mu inside this big intersection of C of V. Okay. So of course, this mu is only defined as, well, this, first of all, this is contained in X. So this mu is an element in X. We can treat it as a function from K to the reals. Okay, so that's clear. And so we need to try to extend it beyond these compact sets. Okay, so the idea in the next few videos is that we now extend this mu from compact to the open and then to the upper L, and then we show that is actually a random measure. Okay, so that's the idea. But before we do that, let's start by doing some little proof of some property of this mu. So let me do the following proposition. So here's the proposition. So last time we proved that on the index, this K over V, they satisfy these nice property. For example, is monotone. So if I have K1 is contained in K2, then each mu V is less than mu V of K1 less than equal to mu V of K2. And when you take the limit, this mu of K1 is also going to be less than equal to mu of K2. Okay, so that's the first. And second, I want to show that it's also subadditive. So mu of K1 union K2 less than equals to mu of K1 plus mu of K2. And the third one, I want to show that, well, from the last time, we need these two compact sets that are disjoint, but not only disjoint, but actually separated by some open sets. So they're, if you right multiplied by some V inverse, then their corresponding mu V is additive. Okay, but since we're now taking the limit, okay, so the idea is that hopefully this mu is actually additive for disjoint compact sets. Okay, so this is what we're going to prove. So if I have K1, K2 there disjoint, then I have the mu of K1 union K2 is actually additive. Okay, so it's mu of K1 plus mu of K2. Okay, so that's what we're going to prove. So now let's prove this proposition. So first of all, let's make the following observation. Because we're working with this X is a product space, so let's observe the following. So if I have some, say, an element F inside this product space X, then the function where I map F maps to the kth component. So here is a function. Basically, it maps from X to the kth component, which is the interval from 0 to k over k0 interior. Okay, so you can think about it as a coordinate map. Well, because your X has the product topology, so this is continuous. But well, this interval, well, you can treat it as interval, but you can also just treat it as real. So you just pretend your the function value evaluated at this compact set K is inside real. So that's going to be continuous. Okay, so that's quite clear. So because of this continuity, so if I consider the first one, so let's say phi 1, let's map X to R by the following. So if I take any F, I map it to F of K2 minus F of K1, where K1, K2 are given, they're fixed. This is going to be continuous. Okay, so it's a difference of two continuous functions. You map it to K1 or K2, they're both continuous, take their difference, still continuous. Okay, So because it's continuous, and we know that for every mu v, we proved from last time that phi 1 of this mu v is going to be mu v of k2 minus mu v of k1. That's non-negative, so that's greater than or equal to 0. So we basically just show that if I restrict my phi to each of these C of B, that's going to be a non-negative value, okay? Always return something non-negative. Because I'm continuous, so on their intersection, basically their limit is going to be non-negative. So basically, if I evaluate at their intersection, that's also going to be non-negative. Okay, so that's how we prove the first one. And the second one is really similar. You basically apply the same argument, except the phi now is basically phi 2 of f. It's going to be phi of k1 plus f of k2 minus their union. Okay, so this one is going to be always non-negative, and you basically apply the exactly same trick. Okay, you get it in the same way. All right, so I'll leave that as an exercise. And the only last one is slightly needs some slight difficulty. So basically, the difficulty is that we only have this additivity when V kind of separates K1 and K2. Okay. So in other words, if I have two disjoint compact sets, if I can show that I can always find a V that separates them, well, then starting from that V on, then I have this mu V is going to be additive for these K1, K2 disjoint. And then in there, we basically now can apply the same argument and show that the mu also is additive for this K1, K2. So we need a little lemma, okay? So essentially, we need the following lemma. So I have for every K1 and K2, they're compact. Inside your group G is locally compact Hausdorff. Then there exists a V that's open neighborhood of the identity, so that you have the K1 V inverse and the K2 V inverse. They're going to be disjoint. Okay, so that's what we need to prove. Well, the proof is fairly simple, so it's slightly technical. So let's do the following. All right, so for every x inside K1, okay, so K1, we can actually separate it to K2 because K2 is a compact set, its complement is open. So there exists, let's say, U of x, okay, open neighborhood of identity. So that the following, if I translate the open neighborhood of x, okay, you translate ux by x, okay, that's going to be disjoint from the K2, okay, you can always do that. And let's pick some symmetric neighborhood, let's pick some Vx, open neighborhood, okay, open, so that this Vx dot Vx is going to be contained in the Ux, let's just say Vx is Vx inverse, okay? So it doesn't really matter. So the idea is we shrink this Ux a little bit, so give us a little bit more room once when we deal with this finite cover later. Okay, so now we do the standard trick. We can cover this K1 by these covers. So for each of these xi, I can cover it by the slightly smaller one, I shouldn't have I here, so just x translate by v of x, okay? So here x is inside K1, so it's certainly an open cover of K1, so I can have a finite subcover, so K1 is contained in the union of x inside K1 of some xi, oops, I should say I going from some 1 to n of xi, v of xi, okay? So I have a finite subcover, okay? And let's let V to be the intersection of all these V of xi, I go from 1 to n. And this is going to be open, and it's open neighborhood of the identity. Okay, that's quite clear. So let's claim the following. So first of all, let's see that why the K1 dot V is disjoint from K2, okay? So if I consider K1 dot V, well, K1 is contained in the union of these xi, V of xi, I go from 1 to n. And then I multiply entire thing by V on the right, okay? So V is contained in each of these V of xi, so this is contained in the union of xi, V of xi dot V of xi, I going from 1 to n, okay? And this whole thing is contained inside the union of xi times u of xi, I going from 1 to n, and each of these xi, u, xi is disjoint from K2, okay? So this is disjoint from K2, so basically I showed that K1 dot V intersect K2 is now going to be empty, okay? You can separate them by a little set V, okay? So now, well, how can I find another open set that separates K1, K2? Well, the idea is quite simple. You do the same trick again to this open set V now. Okay, so let's because V is an open neighborhood, there exists another open neighborhood W that's open. So that W dot W is contained in V, okay, so you separate them again. And then you have this W is symmetric, okay, W is equal to W inverse. Okay, so now let's look at K1W and K2W, and I want to show that they are actually disjoint, okay? So if you have some x inside K1 times, let's say W or W inverse, doesn't really matter, they're symmetric, and they intersect the K2 times the W, then what you have is x is equals to some, let's say, little k1 times w1 equals to little k2 times w2, but that will imply your k2 is equal to k1 w1, and you move the w2 to the other side by taking an inverse. And the way you chose your w inverse is still in there, so w2 inverse in w, you have two copies of w, get something in v. So that's inside K1.V, and you have a contradiction, okay? So basically that shows this is also always going to be the empty, okay? So that implies K1W intersect K2W is always going to be the empty, okay? So that finished the proof, okay? Your two compact set in your locally compact Hausdorff group will always be separated by these multiplication by some open neighborhood, okay? I just want to say that in general, if you just forget about the group structure, if you just have a locally compact Hausdorff space with some topological condition, this same condition may still be true. Okay, I'm not going to go too much into the details of general topology. Okay, so we're using the group structure a lot here. Okay, but in general, the same argument may still hold. Okay, so now we finish this little technical lemma, and we can basically show the third part of our proposition. Okay, so once we have that, so now we have K1 and K2, they're compact and they're disjoint. Okay, so we can show that there exists a V open neighborhood of the identity, so that they are separated by this K1, the K2 are separated by this open neighborhood. Okay, so I have K2 of V inverse that's going to be equals to the empty. Okay, so in particular, I have the following. So if I have every U contained in this V, okay, so then clearly the K1U inverse is also separates this K1 and K2, okay? You get something smaller, so that's clearly also disjoint. Okay, so what you have is that the mu of U, if you consider mu U of K1 union K2 by the last video, we saw that's going to be additive on this K1, K2, okay? So this is additive here. In other words, if you consider the mu, let's just say mu3 of f, okay, basically the same as phi 2 technically. If you define it as your function evaluate at k1 plus f of k2 minus f of k1 union k2, then what you see is that these phi 3 of f, if you evaluate at C of V, where the V is this particular V, okay, this particular V here, not all of them, but a small enough one, then you get something that's equal to 0, okay? Well, but your mu come from the intersection, so in particular, your mu is from this C of V, so clearly the phi 3 of this mu is going to be 0 as well, okay? So mu is additive, okay? So this finished the proof of this proposition.